Thanks, everyone. It's lovely to be here in Malaga, but we're actually having hotter weather in Sweden at this point, which is quite weird. It was not what I expected. But I'm enjoying it here, definitely. I would like to try to give you a sort of a walkthrough how to think in terms of events. A lot of people have probably heard about events. Events have been around for ages, like decades. I started using events myself, like signals and slots and all types of stuff back about 20 years ago when I started programming. But events are sort of have had a real sort of hype the last years, and I think it's for good reasons. They are an immense help when building distributed systems and making sense of distributed systems. So I'm going to talk to you about how to design events first, microservices. So we have our starting point here is microservices. I think most of people here probably know what it is and why one should approach microservices. But just to make it clear, I hope it's for the right reasons. So the primary sort of reason for using microservices should be to scale the organization. I mean, creating multiple autonomous teams that can sort of deliver software fully independent of each other. I mean, deploying features like as fast as each team can go, not in lockstep across the whole organization. That said, microservices sort of forces people to enter the world of distributed systems, and there's a lot of lost opportunity, I'd say, if one doesn't go all in on that. And see, a lot of companies when they go about microservices end up with something like this. So they take their monolith, they replace their sort of regular synchronous method dispatch that they have between services with synchronous REST calls, and they sort of maintain the synchronous communication with the database, etc. Right? And this gives us, this retains the blocking, this retains the strong coupling that we have with the monolith. It does allow, if you do the protocols right, for the organization to scale, right? But it doesn't take advantage of the promise of distributed systems, right? Being able to scale elastically and being able to build fully resilient systems. So I think we need to go about it a slightly different way because of that, because essentially, it sort of maintains the strong coupling, strong temporal coupling, etc. That limits the scale, limits the availability, limits sort of things like extensibility of the system, maintainability of the system, and often the complexity just grows straight across the roof when systems get large enough. They become almost impossible to understand, even less so maintain. So I think we can do better than this. And I'll try to sort of paint the picture of how to think in events and how I think embracing the problem and framing the problem in terms of events can help us get to a lot of these good things as part of that. And I will do that from sort of domain-driven design perspective. Domain-driven design has been around for, was it 15 years or something? It's been now since Eric Evans released the domain-driven design book, the canonical sort of tackling complexity at the heart of software, or what it was called. And DDD, as most people call it, is a great tool. It served us well, right? And it can continue to serve us really well. But it can also sort of lead us down the wrong path. And because if you use this tool sort of in the wrong way in this new world that microservices are and distributed systems are, etc., it can actually cause a lot of harm. And the main problem with DDD and actually with object-oriented programming in general, I mean, the way I was taught OO back in in the 90s is that it puts a focus on structure as the first thing that you should look for. You should sort of try to find all the domain objects. Look for the nubs. Like that's what I was told when in classic object-oriented design. and I think the problem is that it sort of puts focus on structure, the structure of the system or in the design too early in the design process. And by practicing sort of events first design, that can help with that. Greg Young said in one of his presentations that when you start modeling events, it forces you to think about the behavior of the system as opposed to thinking about the structure of the system. And I think it's very important that we don't focus initially on the things, the nouns. We shouldn't go out and try to find all the nouns in our model, but instead trying to focus on what happens in the system, on who's talking to who, how does information flow in the system, etc. Look for the verbs instead of the nouns. And these verbs are very often sort of materialized as events. Okay? But let's take a step back then first. I mean, what is an event in the first place? There might be many definitions of it. I'll try to give mine that perhaps doesn't have sort of an academic sound reasoning to it, but it's sort of based from experience. So the way I look at it is that the events represent facts of information. You know, facts are immutable. If you think about like facts or knowledge in general in the world today, you know, knowledge can only grow. There's no way to retract knowledge, really. We just, you know, we as humans will learn more things, and by adding sort of new facts as we sort of go through life, and you know, this means that events. Here I'm talking about events as fact, you know. So facts, they can be disregarded because it might be, you know, that there enters some sort of fact into the system, or you hear some sort of fact that you simply don't believe. You know, the sender or the communicator might lie, or it might be conflicting with what you currently know. So you have the right to disregard a fact. But the way I view it is that once fact has been accepted as being true, so they can't be retracted. And this means also that events and sort of being as facts can't be deleted. You know, there's a lot of discussions now around GDPR, so there might be sort of practical reasons why you would have to delete events, like from legal or moral reasons. But conceptually, in my worldview, the way I approach this is that events shouldn't be deleted. You cannot retract knowledge. Knowledge only grows, facts accrue, etc. Right? But, of course, existing facts arriving new to the system, new facts arriving into the system can, of course, invalidate existing facts. That's how we sort of evolve as humans or as humanity all the time. We learn more, and then we realize that the model we had in the past is not accurate anymore, and that's totally fine. So I think we should sort of ask ourselves when we come into sort of a problem, the use case. I mean, sort of, what are the facts? To try to sort of mine them like a detective. And one really good way of doing that is through a sort of quite new technique called event storming. Event storming is essentially that you bring all the stakeholders into one room, you hand them a bunch of post-it notes. Stakeholders being, I mean, programmers, domain experts, you know, business people, everyone, you know, that sort of understands the domain, and the people that try to model the domain, all of them into one room, and brainstorm trying to find the domain language and trying to define the domain model through the lens of events, through what happens in the system, trying to understand the causality. I mean, what is affecting what, and why, and what are the steps in between, etc. How does information really flow in the system? Because I mean, this is really the heart of the domain. How do things communicate? What data gets passed along, etc. This is more often closer to business value than finding the things that does something. Okay, so we should try to understand first intents. And so when we come into this brainstorm session, let's say, I mean, one thing that we should look for is intents, and in the intents can often be things like communication, conversation, expectations, the one thing I have on another, contracts between sort of components, transfer of control, where I'm handing over control to someone else to do something. That's usually intent. We should also try to find facts, and facts are usually things like state, history, causality, as we talked about, notifications, and transfer of state. And here, intents are very often then modeled as commands, because commands have intent, okay? While facts are events, okay? So let's now try to understand commands and events a little bit better here, because that's really the heart of events first modeling and events first design. Command is really so the object form of a request, of a regular method, you might say. It's usually phrased in the imperative, like things like create order, ship product, etc. Okay. So let's first try to find them. They usually then cause some sort of reaction in the component or object that receives the commands or accepts the commands. Reactions represent side effects. And reactions are useless without side effect, meaning that they actually do something on the side, causing another command to be sent, storing things in the database, firing off, an email or whatever. And finally, the events. The events represent something that has already happened sometime in the past. It doesn't represent the intent to do something. It represents something that already happened, something that can't be retracted, something that you can choose to react upon and sort of see as the truth or not. They're usually phrased in past tense, things like order created, product shipped. Instead of ship product, you have product shipped, it's already happened, right? But let's dig a little bit deeper here and see sort of the real difference between commands and events. Commands are really all about intent. I want to get someone to do something. While events are completely intentless, they just happen, This means that commands are directed, while events are anonymous. Okay? Commands, they have a single addressable destination. They might be sent to many, but each one represents a single address that I'm sending the command to. I know who I'm sending it to, and I know why. Okay? While events, they just happen for anyone. 1, 0, 200, 1,000,000 to observe. Okay? Commands, they model personal communication. I'm communicating directly with you. I want you to do something. While events, they model essentially broadcast, speaker's corner or this situation. I'm talking to you. Okay? Hopefully we'll have a more engaged discussion afterwards, but now it's more, I'm sort of relaying what I think is facts to you guys. Commands have a distributed focus, They cross address spaces. While events, they have a local focus. They are just emitted where they are, wherever they happen. They might be relayed somewhere else using some sort of protocol, but conceptually they are just local, while commands are distributed. And commands are really all about command and control, while events really helps us to build autonomy. Because events, components that emit events, they don't care who's listening to. They are fully autonomous, fully in charge of themselves, instead of being told what to do all the time. Are you with me? Hopefully. So I think we should let the events sort of define the bounded context. A lot of people talk about bounded context in DDD. And this means, of course, defining well-defined protocols, how you communicate across these bounded contexts, and what promises that we make to the world, and that we will then try to keep. And one interesting thing is by thinking in events sort of inverts the control flow here. Instead of just being fully reactive, in the sense, I'm just reacting to whatever I'm told to do. I'm sort of just reacting to events that I choose to subscribe to. Okay. So what is the characteristics of an event-driven service? I'll try to walk through a little illustration here. Hopefully, a little bit more things fall into place. First, a little bit of theory here. First, event-driven services first receive or react to facts coming its way. Okay. Then they can often do something. Okay. They do some sort of processing, and then they publish new facts to the world, representing sort of the conclusions it came up with, the result of the processing, etc. And they do that in an asynchronous fashion to reduce the coupling between these event-driven services. And as I said before, this sort of helps with autonomy because it inverts the control flow and making components less dependent on each other, which is a really, really good thing in distributed systems. And when I talk about facts, I mean immutable events, just to make it clear again. Okay, so there's a lot of talk about immutability here. Mutable state then. I mean for die-hard functional programmers, there is no such thing as mutable state, right? But to practical or I say pragmatic practitioners, of course, mutable state has its place. I mean, it's often very natural way to think and design algorithms. It's usually more efficient, etc. So I think mutable is fine. Using mutable state is fine, right? But the key thing is needs to be contained, fully contained within the scope of the service. It must be non-observable to the rest of the world. The rest of the world can't know that you used sort of mutable state to do your processing, etc. It needs to be contained in sort of a safe haven of local processing. And then when you're done with your local processing, what you do then, you take the result, you create an immutable fact representing that result, and you publish that to the rest of the world. This means that other components can base their reasoning on stable values, things that they know are true. You came up with that conclusion, you publish that as a fact, as a truth. Other can react to that. Mutable state is the opposite. Things can change just when you look at it. Someone overwrites a record with a new sort of fact. And that's really, really dangerous, especially in distributed systems, right? But actually everywhere. As long as there's not a fully local single threaded system. So to model this sort of isolation, this isolated contained module, we do that usually using an aggregate. The aggregate service is what DDD calls this your unit of persistence, your unit of state. Okay, and that maintains the integrity of the state and maintains sort of the consistency of the state. Both is sort of unit of consistency. It's also a unit of failure, because if this is really important that this aggregate is atomic. What I mean by that is that if it fails, the whole thing fails. If it's replicated, the whole thing is replicated. It can't be like half thing failed and half is up. This gives us partial failures and inconsistent data. If the whole thing is replicated, it means that consistency is fully maintained across the replication process, etc. And the aggregate is, of course, fully autonomous. It can't be dependent on anything else, really. So let's go through a little bit of illustration here. Then. Let's say we have a user. He sends a command. The user here can be another service, it can be a real user. Actually, commands are very often initiated by real users in most applications. You see out there, web apps and all kinds of stuff. But it can be anything, of course, initiating this. So let's say some user sends a command here through REST, HTTP, gRPC, or whatever. And it ends up in this component's mailbox here. That component does some sort of processing, gets a result. We want to publish its new result to the rest of the world. It does that in an asynchronous fashion by sending it to the event stream through the event bus. Okay? The event bus then sort of relays that to whoever might be listening. Might be 0, might be, as I said, 2, 3, 5, 1,000. It really doesn't matter. Whoever's interested will get that in its mailbox then. They can do their processing, publish new facts, etc. Cyclic dependencies here are usually very, very common. But for example, sending a signal back to the user that the full sort of work has been completed across all components, etc. It can also be that it's actually not a service here, but like an external database, like HDFS, for example, or something. I mean, it might be picked up by Hadoop for overnight batch processing, etc., getting more results out of all this data that we're generating. Or it might be some sort of external system because often the event bus and the event stream here can be used as integration, to integrate with third-party systems, etc. Okay? What's really important here, though, and what takes the leap of faith, right, is that all of this now is eventually consistent. Because things are happening asynchronously. So it will take a while for all these events to propagate. But if you think about how the real world, I mean, that sort of how the real world works is actually very often the case. I'll dive into this a little bit deeper in a second. So we can use the event stream as soon as we have an event stream. We can use it for a ton of different things. Like we can use this as a communication fabric between components, between systems, etc. We can use this as the integration fabric, as I said. We can use it as a replication fabric to replicate these, you know, for redundancy. We can use it as the consensus fabric, try to make sense and make sure that we have a consistent view, an eventually consistent view, but still a consistent view of the data. And we can use it as a persistence fabric, as I will dive into deeper later. So the event stream actually turns out to be very useful if you have modeled your world in events. So events as persistence. A lot of people might think that what's wrong with CRUD, right? What's wrong with using just an Oracle database, etc., etc. And I'd say there's really nothing wrong per se with CRUD. I mean, CRUD served us really well. It works great for monoliths, for example, and for traditional JE applications, etc. But it's really hard to build systems that are that keeps up with guarantees distributed systems using CRUD, let's say, because, you know, as I said, CRUD's fine for isolated data. But in a distributed system, there's very little isolated data. I mean, it's very seldom services never communicates with anyone across some sort of workflow or some sort of transaction. Okay? But the thing is that cross-CRUD services consistency is extremely hard because you can't do joins. You know, joins, we take joins for granted in a local system. They're easy, they're reasonably cheap, and they can have so much power. But, you know, multiple services each having their own isolated database, as you should do with microservices, you can't easily do joins across them. Okay? And you often end up, if you try to stitch these together anyway, you often end up with sort of ad hoc and often very weak consistency guarantees across your services. So I believe that, I mean, very often we feel like Calvin here, right? Reality continues to ruin my life. And the reason why this is that, you know, transaction doesn't work that well in distributed systems. And there is a lot, I would say, there is a lot of very interesting work being done today. You try to bring distributed transactions back, but it's very early. It is sort of promising when Google Spanner, for example, etc. But I'd say that it's nothing that I think we can bet on at this point. And I think we should instead of try to design our systems around how the world actually works, instead of trying to shoehorn them once again into a sort of model that suits us as developers better. Then it sort of serves the real world. So Patel once said, you know, that two-phase commit is the anti-availability protocol. It's really, really hard to make transactions available. And you know, you have the sort of also often, very often poor scalability. It increased contention. Contention is the biggest scalability killer. So it sort of often puts a very hard sort of ceiling on how your system can scale, etc., right? And the thing is, I believe the strong consistency is nothing wrong with that. Of course, that's really makes things a lot easier. But it's the wrong default in distributed systems. So if you use it very, very sparingly, use it carefully, only where you absolutely have to, and as a way of sort of opting in on, instead of opting out on, okay? So what can we do then instead? Yeah, we need to rely on eventual consistency again. And we should be really surprised about that, because it's really how the world works all around us. I mean, everything we sort of experience are eventually consistent, okay? We really need to sort of embrace reality instead of trying to fight it and shoehorn it into our little world of computer science, like we constantly try to do. It's worked like surprisingly long, to be honest. So I mean, you know, it's actually a fact, you know, that information travels at the speed of light, and that sort of puts a hard limit on the speed of information. You know, this is a reality in systems today. This is not really some esoteric thing. I mean, this actually affects systems that we build every day. This latency that information has traveling from A to B is actually a fact that information is always from the past. Everything we experience, like feel, see, hear, you know, is from the past. It has already happened, often quite some time ago. We just don't think about it like that. You know, so in a way, we're always looking into the past. It's always in the eye of the beholder. This means that the present that we experience is actually relative. It's relative to us. You know, there is no such thing as globally consistent now, even though we try to sort of make that work. And it's also a fact that, you know, as soon as we exit this boundary, you know, of our service, we sort of enter this wild ocean of non-determinism. Okay, that's the world of distributed systems. The distributed systems, you know, they can be really scary. You know, it's the world where information gets lost. You know, messages get dropped. Where information gets garbled on the way, etc. Where failure detection is really nothing but a guessing game. It's really, really hard to even know if the guy with the one I'm communicating with is down, or if it's just being slow, out for lunch, you know, we go do GC or something like that. And this might sound terrifying, but it's also that this world is the world that gives us solutions for things like scalability, for things like availability. A single thing can't scale by definition, an atomic single thing. A single thing can't be available by definition. You need multiple ones, and you know, and there you have a distributed system. So, and we need to. So what we need to do is better tools, I think, to model this uncertainty we have between our components, this sea of non-determinism. And Pat Helen said that in the system which can't count on distributed transactions, the management of uncertainty needs to be implemented in the business logic. It needs to be modeled into our domain. Okay, we need to find a better way to model this space in between services. It's not taken care of for us. I mean, it doesn't help just putting your stuff in Docker containers and throw them out on Kubernetes, right? That doesn't solve that problem. We need to design our system around a way to do this in the same fashion. Okay, and we do that often by making hard things explicit. Don't try to hide them. We've been trying to do that for too long. I mean, RPC trying to hide the network really doesn't work that well. Distributed objects, you know, EDBs and Corba, etc. Trying to make local, I mean, distributed look like local is usually a bad thing. It's better to go all in, embrace the constraints of reality. And then we are in the shape actually to manage that. So that's my philosophy, right? And I think the events can lead to greater certainty because this gives us a way to model this space in between. It means it gives us a way to model this uncertainty between components. And events can also sort of help us then craft sort of these autonomous islands. These islands, you know, these are safe zones, you know, of determinism and strong consistency. Because within each service, if we build it right, we can actually have strong consistency. We can get sanity back. No, we can get determinism back. It's just as soon as we exit the service, hell breaks loose. Sorry, I didn't say that. But things get hard, you know. So the question is then, I mean, how do we work with communication and data across all these services? And how do we ensure consistency? How do we ensure consensus? Yeah, the hero of the talk here, Pat Helen, once again has, I mean, sort of, I think, has a very good way of thinking about this, where he states that inside data, the data within your service, that's our current present, that's our now. Okay, that can be strongly consistent. That can be deterministic. Okay? You can use mutable state. You're in safe zone. That's our state within the component. Okay, outside data, that's what he calls the blast from the past. That's That's where the events that arrive from other services and other sources. That's the facts arriving into our component that we can react to. And between services, So Pat Allen calls that hope for the future. It's almost poetic, right? I love this. And that's our commands. I mean, others sending intent to us, hoping that we will comply, so to speak. Okay. And in a way, you know, the system of microservices is really sort of, if you build it using events and event streams, it's really sort of this never-ending sort of stream toward convergence. The system tries constantly to converge, but it never ever gets there. It might get there for a split second, but then it's off again. Okay? Because it's really important to understand that there is no now. No now meaning a single now across, unless you sort of lock your whole world, or stop the world type of thing, which of course doesn't really work. So, event-based persistence, I think, is a much better way of dealing with this than sort of reaching for the closest thing that we know, being CRUD, being Oracle databases using create, read, update, delete, etc. Okay? And the thing is that I think we can still use CRUD together with event streams and get, not all the way, right, but a little bit on the way. So I think the first step is not just to throw out all CRUD and just go all in on events. The first sort of practical way is often to sort of enhance your CRUD services using an event stream. Because if we do that, we can actually get consistent, because it's a materialized view. And what I mean, I'll try to illustrate here. Let's say we have service A and we have service B here. They both CRUD services, storing data down in table A and table B here. And let's say that both of these have an event stream attached on the side. If then service A then sort of wants to update a row in table A, it does that, but it also creates an event representing that change and sends that off to the event stream. It's very important that you do this in a fully atomic fashion. We have some sample code, you know, on Lightman, Tech Hub, or GitHub repository for how to do this. We'll probably wrap that in the frameworks to come. It's not that hard, but it's very important to do that in an atomic fashion. Service B here then does the same. Stores something and pushes it out sort of onto the service bus. Now we have a service C that's interested in what's happening in service A and service B. You know, it can then subscribe to these two event streams, okay? And once it gets the event, it can then sort of join. So, I just wanted to jump one back. I'm sorry. I'm a newbie when it comes to these things. Oh, anyway. Enjoy the learning experience. Okay, so here we go. It can then join table A and table B, sort of based on the events that are flowing in. What's really important here, though, is that it can only serve that as read-only, of course, because the source of truth is is back here, service A and service B. So whenever a user here wants to communicate. Wants to understand sort of the full scope of this sort of joint transaction, it just goes to service C and gets that. Okay, so this is a first step towards a pattern called CQRS, but it's even more important that it's a first step away from CRUD. Okay. Once again, I mean, this is eventually consistent, right? So there is a chance that it's not read your writes here. I mean, that the user actually writes to service A, and then it reads, and the data hasn't made it to service C, right? But as I said, if you know that, you can take precautions for it, and it's very often modeled how things work in the real world, because nothing is instantaneous, right? Okay. But I think we can also do better here. We can try to move even further away from CRUD. I mean, Jim Gray once said that, you know, updating place strikes systems designer as the cardinal sin. Okay, it violates accounting principles that have been used for hundreds of years. And the real problem here is really updating place, destructive update, that we overwrite existing facts with new facts, with discarding the existing fact without sort of having a way to get back to that. Okay? And yet again, I think we need to, if we want a better approach than we currently have, often we need to just look back at how the world actually works. And in this case, relearn basic accounting principles. How does accounting work and has worked for hundreds of years? Not by overwriting records, but appending knowledge, appending facts, potentially invalidating existing ones, right? Papelin again said that the truth is the log, the database is the cache of a subset of the log. The question is, why continue to work with the cache of a subset of the real thing? In this case, an Oracle database, a Postgres database, or whatever, when you can work with the real thing, the log itself. Okay? There is a reason why we use the update in place, I may say. Disk space used to be very, very expensive. So there's a reason. But today, the disk space is immensely cheap. There's really no reason to continue to do destructive updates, erasing existing data, and often then have to keep yet another set of tables for historic data, for audit logs, and all kinds of stuff, I believe. We should just use the real thing directly, use the log directly. So I think the event logging here, in the event stream, looked at it from a persistent view, can really be the bedrock on which we can build a lot of things. We can really be the bedrock for consistency, for availability across the system, for scalability, for traceability, for debuggability, and all these things. So event logging sort of simply means that we store each state-changing event in the log, okay, in order, durable on disk. Just transactions in the ledger, okay? And one very common pattern that sort of implements that, I'm sure you've heard of, is event sourcing. Event sourcing sits on top of the event log. And it's really a cure for this cardinal sin update in place, because it never throws anything away. You log in event sourcing, you log every single state-changing event in the component as an event that you store to disk. I'm saying state-changing event. It's not necessary to store all events in the purpose of event sourcing. Only the ones that update your internal component state. Okay? And yeah, the interesting thing is that the way it works, let's take the habit path first. Let's say that we first receive and verify a command that comes in. Let's call it approved payment. Then we create sort of a new event, payment approved, out of that. Then we sort of append that to the event log in a safe fashion. When we know that has happened, then we update the internal state with what we already know has happened. And finally, we run the side effects representing whatever happened, okay? Or the side effect representing the command that came in, okay? In the sad path there, when we for example, want to recover from failure, or want to do replication, for example, which is actually not a sad path, but it has the same code path, is that then we simply rehydrate the events from the event log, bringing the component up to speed where it was when it failed. And yeah, essentially, we do not run the side effects, because they have already been run once. The only thing we need to do is bring the component up to the state it was when it failed. This is what Martin Fowler often calls memory image. And some of the benefits here is that we have one single source of truth, not like scattered across a bunch of tables or a bunch of databases, etc. All history is there. This means that, but first, it allows for this memory image thing. You have like very fast, sort of pure memory access to your data, but it's still persisted on disk for full failure recovery, etc. Okay, and this also sort of avoids this, this classic object-oriented relational impedance mismatch, where you have to sort of map your object to tables and all that mess that creates, Hibernate and JPA and JDO and everything that we've gone through. There's really no reason to do that anymore. Okay, it also allows others to subscribe to state changes, like we've seen before, if we use the event stream here, for integration purposes, for replication purposes, and all things. And yes, it actually also tends to have really good mechanical sympathy here. Adhering to the single writer principle, you can have one single thread in this writing in an append-only fashion to the log. Very much in line with how modern hardware works, etc. Right? So, how much time do I have left? 3 minutes, okay. I can just quickly go through CQRS then, because we've also hinted at it with this sort of additional event log on the side of our services. Going all in on CQRS can actually be a good thing if you go all in on events. CQRS was sort of a pattern that Greg Young invented or coined. I don't know if he actually invented it. It works great with event sourcing, even though it's a general pattern. It sort of allows you to separate your reads from your writes, or rather say the read model, the way you model the reads, from the way you model the writes. They often have very different characteristics. Both how you model them in the domain, but also, in terms of scale, in terms of availability, in terms of users' characteristics. Instead of lumping it all together and trying to, for example, scale it as one thing, here you can say if you have a very sort of read-heavy system, you can scale the reads fully independent of the writes, or vice versa, right? So you have more knobs to turn here, and most importantly, it allows you to store each model in its optimal format. The optimal format for is often event logging if you use events, using event sourcing, but event logging is really hard to query. An event log is hard to query, right? So, but by separating the read model from the write model, it means that the read model can still be a SQL database. You can still put it in a SQL database or a graph database, or you can put it, in Hadoop for batch processing or Spark streaming or Flink or whatever. And the way it works is that you have this user here sending a command now to the right side. The right side write the events, in this case using event sourcing then, to the event log. The event log, yet again, publishes things to the event bus. And here, the read side sort of stores that in a database. For example, in this case, using CRUD, using Oracle. And then serving the read side model over to the user that can query it in the way, it is used to. So this very often creates the best of both worlds, even though it adds more complexity, of course, and it feels alien to a lot of people. I believe that if you go all in on event sourcing, it's definitely something to take a look at, even if you do so gradually. Okay. So that's it. I was just going to wrap up here. I had a few more slides, but I'm running out of time. So I was going to say the key takeaways here, I think, is that with the event-sourced design, it really helps you to reduce risk. Everyone wants to reduce risk when they move to microservices because it is risky business. It helps us move faster to resilient and scalable architecture, going all in on distributed systems instead of just ending up there, as an accident by going to microservices. You actually, you're in charge of where you want to go, and you go all in on distributed systems in order to design fully autonomous services. And I think events really help you to balance these things like certainty and uncertainty. Have good boundaries with your services and model this space in between the uncertainty in a better way. And also event logging, if you go all in on that, helps us avoid things like CRUD and ORMs. I'm sure a lot of people have had pains with that. It allows us to take full control of the system's history, how to replay the log. You have full bulletproof audit log right in the log instead of having to duplicate that work somewhere else, etc. When replaying allows for things like time travel, which can also be interesting for debuggability, for understandability. Why did something go wrong? You just replay the event log to find out, etc. And it really helps balance strong and eventual consistency so you can get the best of both worlds. Okay? That's all I had. Akka is, of course, a tool that can help you with all of this. I'm not here to pitch that specifically, but please come up to me and talk about Akka if you're interested. I also wrote a little book about this, Reactive Microsystems. It's free. It's just one of those O'Reilly mini books you can download freely, available from this bit.ly link here, or just send me an email, Jonas at Lightman, if you want to discuss this further. So thanks a lot for your attention.